Okay, exercise number 3. We are supposed to show that these statements are all equivalent. First, G is abelian. Second, the inverse of A dot B, or simply AB, is A inverse B inverse. If you remember in proposition 1, we showed that in general the order is switched, so we have B inverse times A inverse, but if G is abelian, then this is the same. Or that this expression here, which is called the commutator of A and B, is the identity, or that AB squared is the same as A squared times B squared. All right, instead of showing that these are equivalent, these are equivalent, these are equivalent, and so on, we go one time in a circle. We show that from this follows this, from this follows this, from this follows this, and then we shouldn't forget that from this we have to show follows this. So we go one time around in a circle, and then this also shows that those are equivalent. Because if I want to show that from this follows this, I know that this implies this, implies this, implies this. So it's the same as showing the other way around. All right. So here we suppose G is abelian, and we have to show that. This is easy because by proposition 1, we already know that this is the general formula for the inverse of a composition of two elements. And now if G is abelian, I can switch the order, and that's it. So here you should note proposition 1, and here you should write G abelian. So maybe like that. And this was our assumption. All right, next step, we assume that this here is true. So we have this formula, and we have to show that this here then is true. Now if we have this, we can simply multiply with AB from the left. So we take AB, which is an element of the group, and multiply this equation here from the left with AB. So then, because multiplying by a group element is a map, if these two are equal, then the image under this map must be equal. So again, we have equality. And here, this, of course, by definition of the inverse, is the identity. And here, by associativity, we can drop the parentheses. So we have AB, A inverse, B inverse, and this is what we wanted to prove. Next, 3 implies 4. We assume that this here is true, and we have to prove this. All right, so first of all, by definition, something squared in a group means this element composed with itself. I speak of multiplication, although you shouldn't confuse it with normal multiplication. So we have this, and again by associativity I drop the parentheses. For the umpteenth time, if you're a beginner, and this is one of your first exercises that you hand in, please do all these extra steps and write down. We have the parentheses here, and by associativity I can drop them. Now we are here, and now we want to switch those places. If the A were here and the B there, we would end up with A squared and B squared. How do we do that? So, all right, we know that this here is true. If I multiply that from the right with B, I end up with here, by associativity, I can drop the parentheses, and B inverse B gives me the identity, which I can leave out. And then again, I multiply from the right with A. So we have AB equals BA, which is just the basic condition of commutativity, but formulated in a different way here with this relation. And now I can switch those two here. So then I end up with AABB, which is A squared B squared. And again, if you're a beginner handing in this as a solution to an exercise sheet, you should always write here, because we have to show something for all elements. You write here, let A and B be any arbitrary element of G. Then it would be perfect, because here I do not specify what A and B are. So by assumption, 4 is true, so we have that, and we need to show that the group is abelian. So let's spell it out. So this here means AB times itself, and this here means A times itself times B times itself. And now proposition 3 actually saves us some effort, because we know in any group there is the cancellation law. If those two are equal, I can cancel here the A, and in the same manner I can cancel the B from the right hand side. So this here is equivalent to BA equals AB. Actually, proposition 3 only shows this implication from here to there, but of course multiplying by A from the left and by B from the right gives me this equivalency here. And it doesn't actually matter, because this direction is enough. We only want to go from here to there. We don't even need the equivalence. And now, since A and B were arbitrary elements, you should really write that down here. Let A and B be arbitrary elements. Then we have, from this here follows that, and this is just commutativity of the group. All right. Those were also not very hard or creative arguments, but I think for a beginner, this is already a, maybe not advanced, but a medium level exercise, especially understanding all the logic and writing this down here in a, let's say, clean and understandable way. This is not so easy. All right, let's do exercise 4 quick before I run out of battery. This is already a hard exercise, in my opinion, for a beginner. We have the weakened group axioms. Here in short, there is only a left identity element, and there are only left inverses. And we are going to show that this is actually equivalent to the existence of an identity from both sides and inverses from both sides. So it would have been enough to formulate the group axioms like that. But this is rather more a theoretical exercise. But it's good to know that from left inverses and left identity already follows the corresponding right identities and left right inverses. So we have to show that these two weakened axioms are equivalent to group axioms G2 and G3, always assuming that dot is an associative operation. Of course, this is trivial if I have identity and inverses from both sides there, especially from the left side. So this is the interesting implication. We assume that those are true and have to show G2 and G3. Now we're following the hint, we prove G3 first. So we take an element A in G and let A prime be its left inverse. So this holds, and we have to show that then this follows. And if you don't see the right trick, this is not so easy. So we start with A prime, and now we insert an identity. This is always possible. If we would write this as A prime A, this would not help us at all, because then the A's would meet. I have A squared and the A primes outside. But I know that also A prime has a left inverse. A prime is also an element of the group, and all the elements of the group have a left inverse. This I call A double prime. And by associativity, I drop all the parentheses. I would have to put parentheses here and here, but I can drop them. Remark that over your equal sign. And now A prime A is the identity by assumption. And we are left with A prime, A double prime, A prime, but A double prime is the inverse, the left inverse of A prime. So this is nothing but the identity, and we are done. If you came up with that yourself and you're a beginner, you have never seen this trick before, please leave a comment and congratulations. That's already a neat idea to see that you actually need the left inverse of this left inverse of A. And then we get inverses from both sides. Oh, what I forgot, of course, here we use that there is a left identity. Would not have been possible to put the E from the right-hand side because we only have a left identity. Now for G2. So we assume we have a left identity, so for any arbitrary A in G, I'm a bit lazy here, you should write down let A in G be arbitrary and E dot A equals A. And we have to show that then also A times E equals A is true, so that E is a right inverse. So here it is, A in G is arbitrary, and then we have shown it for any A in G. Okay, this is not so hard. We have E can be written as A prime A prime being the left inverse, but we also know it's also the right inverse. By associativity, let's do it, let's write it like that. So by associativity I can move the parentheses, and now we use what we have just proven, namely that A prime also is a right inverse to A, so we end up with E times A. So this here because E is a left identity, and then we have shown that E also is a right identity. And now we really deserved to put this proof box here because again this is not an easy exercise, at least. Okay, we're not done yet. We're supposed to find a non-associative example of a group where there is a left identity but no right identity. We already know that from exercise 1. So to show you how important associativity is, because we always treat it lightly and say, well, we can leave the parentheses, blah, 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 associativity. Here we have convinced ourselves in exercise 1 this is a non-associative operation on the integers. Oh, I might have switched the order in exercise 1. Not sure. So we take this operation here. So 0 is a left identity because 0 composed with B is B minus 0. B stays the same, but not a right identity because A composed with 0 is minus A. This is not the same. So, and these proofs rely heavily on associativity, even if we treat it lightly here, because this is a non-associative operation. It is not true that from left identity it follows that there must be a right identity. So you should always keep that in mind. Associativity is important, mostly in subtle places in those proofs. All right, exercise number 5. We are classifying groups up to order 4. And since we barely have any theory at all, we have to use a pedestrian approach and simply play a group Sudoku and write down the possible group tables. Of course, for a set with one element, this is trivial because we define the operation to be E dot E equals E. So E is the neutral element or identity and its own inverse. And this, of course, is associative, so we have a group. And obviously there is only one possibility. So there is one group of order 1. All right. A tiny bit more interesting but still trivial is the case of order 2. 2 elements. One of them must be the identity. This one I call E. The other element I call A. Now let's write down the group table. Since E is the identity, this is all clear, because composing with E must leave the element unchanged. And now A composed with A must be the identity, because otherwise A would have no inverse. So here A is its own inverse. This actually is a group table. The group is commutative, as we can see, because we have symmetry to this diagonal. And associativity is not evident from the group table, so we would have to check it, which of course we don't. But we would have to check, for example, that A dot E is the same as A dot E, and so on. But of course, this is just a big nuisance to write it down. But it's important to realize that this is not clear. If we find a group table that works, that doesn't mean that the operation here has to be associative. So, but for the rest of this exercise, we assume that all the operations we write down are actually associative. So this here is the one group of order 2. There is no other possibility. Now let's see if we can find two different groups of order 3. The elements I call E, A, and B. The first row and column are always trivial because E is the identity, so we simply fill it out like that. Now, very important, in each row and each column, every element has to appear exactly one time. So let's see. A times A could be E or could be B. If it were the identity, this would force B times B also to be the identity, because we can have two identities here. Why? Because if I had two identities here, then A times A would be the same as B times A. So those would be the same, and by the cancellation law it would follow that B is A, which it is not, because we have a group with 3 elements. So here I must have A, and here this doesn't work because I need B, but this cannot be because I already have B. So this is not possible. So the only possible choice here is B, and then this leaves me with E here. And now here I need to have E because of this column, and here I need to have A. And now this is a consistent group table. I have commutativity because the table is symmetrical to this diagonal. Every element has an inverse because here B times A is E, and of course because of commutativity A times B is E. So A and B are inverses of each other, and the identity is, as always, its own inverse. So this is a group with 3 elements if this operation is associative, which it is, which we are not going to check, as I said before. Okay, now the first really interesting case, groups of order 4. There's a hint. We first need to show that there must be an element which is its own inverse. So we try to do this by contradiction. We assume that for all elements A, B, C, which are not the identity, their square, so G composed with itself, is not equal to the identity. And this means exactly that the element isn't its own inverse, because G times G equals E means exactly that G is its own inverse. So, but A must have an inverse. This cannot be A itself by assumption. Of course, it cannot be the identity, so it must be B or C. Without loss of generality, we assume that the inverse of A is B. But then the inverse of B is A, all right? Because we have here A inverse is B, so this means exactly that, and that also means that B inverse is A. So the remaining element C must also have an inverse, but what is left? It cannot be B, it cannot be A, of course it can't be the identity. So C must be its own inverse, which means that C times C is the identity, or C squared is E, which is a contradiction to our assumption. Hence, our assumption was wrong. There is an element that raised to the power of 2 or multiplied by itself gives me the identity. Okay, so we can start filling out the group table. As always, the trivial first row and column. And now there is one element that is its own inverse. We take this element to be A because this can't make any difference. A, B, C are completely gleichberechtigt. So we start with A times A equals E. Then A times B could either be B or C. Of course it can't be B, because if I had B times A equals B, then by the cancellation law this would mean A is the identity, which is it not. It is not, so we must have C here, and besides, if it were B, we would have B twice, which is not allowed. So, and then here there's only one choice left, which is A. So far there is no choice if we take A to be the element which is its own inverse. So we are left with this 2 times 2 square. Now B times B could actually be E, the identity, or it could be A. And both cases are actually possible. Okay, so in the first case we have B squared is the identity, so B also is its own inverse. This forces C squared also to be the identity, because here or here we can't have the identity, because it would appear twice in one row or one column. And then here I must have B, and here I must have B. So this gives me a complete group table. The group is commutative because of symmetry to this diagonal, and all the group axioms are satisfied. What we haven't checked again is associativity. Convince yourself by taking one example that actually this gives you an associative operation. So this is one possible group of order 4. And there's another possibility. B times B could also be A. Then here I must have the identity, because this is missing here. Remember, each element must appear exactly once in each row and each column. And here we also must have the identity, and this leaves me with B here. So here there's exactly one element which is its own inverse, besides the identity of course, and here all the elements are their own inverses. And this also is a commutative group because of symmetry, and those are obviously different operations on the same set. So we have found 2 different groups of order 4. Both of them are abelian. And here again you would have to check associativity by brute force, writing down all the possible combinations. And what would have happened if we would have chosen B to be the element with B squared equals E? Then at first glance we get another different group table, but after renaming, of course, we end up with the same group as here. So this is not really a new group of order 4, but those are really different. Later we will see those are the two different abelian groups of order 4, namely this thing here, z modulo 2z times itself, and here z modulo 4z, but we'll get to that later. So just that you have seen this notation.